I'm Itai Seggev, and this is a little follow-up to the first What is New in Calculus talk, which unfortunately had some technical difficulties. So let's just jump right in. I'm going to talk about the various additions that have been made to calculus over the past year, some very elementary stuff, some more advanced stuff, and then at the end I will talk about some ongoing work that we're going to. So difference quotient is a very, very simple function. It's really just a small convenience. It's the thing that gives you the f of x plus h minus f of x over h. But you can do second order difference quotients. You can do multivariate difference quotients if you so desire. But it's a named thing. It's a good thing to have. So what can you do with the difference quotient? Well, of course, you can compute a derivative. So I have a function g here. And if I take the difference quotient, I get that expression. And when I simplify, when I take the limit as h goes to 0, I get the derivative as I just verified there. One of the cute and somewhat underappreciated facts is that you don't need to compute the first derivative in order to compute the second derivative. If you compute the second difference quotient and take the limit as h goes to 0, assuming it's a nice C2 blah, blah, blah function, then you end up with the second derivative. Of course, you can also take the difference quotient of the first derivative, that's the direct definition of the second derivative, and the limit as h goes to 0 of that is the second derivative. Another nice application is visualizing the derivative. So I have a function here, and then I've defined the tangent with base b and distance h of x using difference quotient. And then I can create a nice manipulate here, and I can move my base point b around. And then as h goes to 0, I end up with a nice tangent line. And of course, on the other side, h can be negative. And either way, we approach a tangent line. Measures. So in version 10, we had arc length, area, volume, and region measure, of which arc length had a special form for parametric formulas. So I have arc length here of r cosine of t sine pi of t as t goes from 0 to 2 pi. And the assumptions are that r is greater than 0. And lo and behold, the arc length of a circle is indeed 2 pi r. And in 10.2 or thereabouts, about a year ago, we added parametric forms for area and volume. So here I integrate t from 0 to 2 pi and r from 0 to 1, and I end up with pi. Or volume, I now have 3 variables for my region and go from there. Well, with version 11, we added this parametric form to region measure. So, or was that 10.4? Sometime recently, we added it. So now in any dimension, including higher than 3 dimensions, you can find the volume of a parametric K region. So one of the advantages of this parametric form over the more familiar region form is that you can use non-Cartesian coordinates. So here I have a surface of revolution, which is this nice nut shape. And that's very easily expressed in cylindrical coordinates. So I can ask for the area as z goes from 0 to pi and theta goes from 0 to 2 pi. If I integrate over all 3 variables, I get the volume of the nut. So those are some nice... Oh, sorry.
Question about arc length. Does it work in 2D, for 2D curves or for
ND. So the parametric form will take an arbitrary dimensionality of the embedding dimension and assume one parameter that you're varying in the embedding.
It may not lie in a plane.
Right. So if I if I change this example here to be, if I added a z component here, sine of t, then now I have a little sinusoid going up and down around a circle, and you end up with an elliptic function apparently. But right, and I could have done 5D whatever I wanted. And there are examples of that in the documentation, including in a sphere that's not embedded in Euclidean space. So you stereographic projections on an n-sphere. Okay, so those are some nice relatively calculus 1 through 2 or 3-ish sorts of examples. Myergy reduce. So Devendra talked about, he sort of really briefly hit upon it, but was mostly talking about Mellin transform. But we have Myergy reduce, which takes functions and expresses them in terms of the Myergy function. Myergy is a generalization of the hypergeometric function. And Beals gave a nice characterization in a paper about earlier this year, actually. Sort of it's the set of generalized solutions whose series solution only requires a one-step recurrence. So this is fairly abstract stuff, but a nice application of that is integration over the reals. So if we have a product of two functions, we might try to re-express both of them in terms of Myergy. And the reason for that is, and that looks a little small to me. Should I, oh, I know, because I crashed my magnification. I didn't restore the magnification. That looks better. There's a nice theorem which tells us that the integral of a product of Myerg's over the reals is in fact a third Myergy function. So if I have this product of two functions on elliptic k times a power, then I can integrate that. Oh, I did not actually evaluate the second rule. I get that, and I can compare with integrate, which will produce a very different looking sort of answer, but it is in fact the same answer. Okay. Another nice topic is the green function. So green function computes a response to a delta forcing function. And the utility is that for linear equations, then arbitrary forcing functions can be solved using convolution. So a nice basic example is you have an RL circuit. And so we have here just sort of the right-hand side of the equation, the operator part. And some initial condition, and we ask for the current as a function of time. Now, for some different forcing function, say sine omega t, then I can just integrate the product of the Green's function with the forcing function, and I get a solution out, and that sort of it goes towards some sinusoidal steady state after some initial, motion. Another example is an inhomogeneous wave equation. So here I've defined the Green's function in a sort of classical notation where I have one set of a pair of variables separated from another pair of variables. And this is the solution to a delta function for the wave equation. And if we plot that as a function of x and t, we get something which looks like that. But I think it's easier to understand if we plot a function of x as a function of time over time. So we have a little pulse at t equals 0 at the origin, and that pulse spreads out uniformly over time. And again, if I have some sort of forcing function, for example, this forcing function here, I integrate that against my Green's function right there, and it'll think for a little while and eventually give us an answer. And so you can see that the solution is the string that's being forced is always sinusoidal, but the amplitude increases over time. And DSolve value would give us the same answer to this equation. And it's clearly not just convolving with the Green's function since it evaluated so much faster. Yes. Okay, Eigen System. Devendra gave a very nice talk yesterday, so I'm just going to briefly mention what it is and give one example. It gives the eigenvalues and eigenfunctions of linear differential operators. So we have here a Laplacian on the interval 0 to pi, and with boundary Dirichlet condition, so it's forced to 0 at the endpoints. And the eigenvalues are 1, 4, 9, and 16, because its sine of x is 0 at both endpoints. Yes, sine of x is equal to 0 at both endpoints, and minus its second derivative is, back to sine, and so on. So a fancier example is the isotropic harmonic oscillator. So I have Laplacian in 3 dimensions plus a constant times sum of squares in the variables, and I specify Dirichlet boundary conditions. This is really saying that this is going to 0 at infinity, because when I solve, you'll see that I say x, y, and z are in full regions of 3. So that means over all of our, solve this over all of our 3, and we get, so this is a system which we asked for the first 8 eigenvalues and eigenfunctions. And this is a system with some degeneracy. So there's a unique ground state, but then there are 3 eigenstates with at the second energy level, basically 1 along each axis. And then there are 5 at the next level, and so on. And here's a nice visualization of the different eigenfunctions. Okay, so DSolve, again, Devendra gave a very nice talk yesterday about all the enhancements we've made to DSolve, but I thought it would be useful to go over those here. Integral equations, partial differential equations over regions, an assumptions option, solutions to Sturm-Liouville problems, a green function solver, so you can explicitly request via method option that it try to use green function. It's also used automatically in some cases. And so one of these nice examples, one of the enhanced PDEs, we have a particle in a one-dimensional box. And so the general solution is just the sum of phase times sinusoids with arbitrary coefficients C of k. And if we give one of those eigenstates as an initial condition, then we get a stationary state, just this pure phase times the one sinusoid. And it has unit integral because it's a properly normalized state. But if we give it a sum of 2 eigenstates, or really any other function other than one of the eigenstates, now there's going to be sort of non-trivial dependence in the mixture between the 2 states, and you can see that the probability density over time changes as the particle bounces back and forth between the walls of the box. Okay, so that is what's in 11.0. You can all do this today, and these are some stuffs, and so now I'm going to need to switch from my normal kernel to my development kernel, because this is stuff that will be coming in 11.1. So we can now take derivatives of symbolic order. So if I ask for the nth derivative of x, it'll tell me that derivative is 1 if n is 1, but it's 0 if it's any higher order of derivative. And D is assuming that n is a positive integer. So really, it's only 1 or 2 or higher, and you really do get 0. For example, if you do cosine, then you get the n pi over 2 as you cycle between the 4 functions. And so there, if we make a table of values, we get the minus sign, the minus cosine, and all the way back to cosine. So a nice example of this is taking the nth derivative of sine. Now I compute the nth term in the Taylor series. So I replaced x with x naught, and then multiplied by x minus x naught to the n and divided by n factorial. And if I sum the series, lo and behold, I come back to sine of x. So it's good. Entire functions really do some to their Taylor series. Another application are sort of formal differentiation rules. So this is the nth derivative of a product. It's a binomial times, a sum of binomial coefficients times the respective derivatives. If I create a table of that, you'll notice it comes back as an inactive sum because otherwise, well, it may or may not try to sum things, but we don't really want these to all expand out. If we activate that and then make the table of the first 3 values, we get the familiar product rule, but then the possibly familiar second order product rule and the rarely written third order product rule. There's also a generalization of the chain rule. I believe this is Fau-di-Bruno's rule. Fau-di-Bruno's rule. And it looks very complicated, but if we, again, make a table, then we have, easy to understand formulas. The first one is clearly the normal chain rule. Second one, we get the product of differentiating f, and therefore we get a second g and it's squared, or we differentiate the g prime, and so on. And so this is something that will definitely make it into 11.1. Other things we're currently working on are index derivatives, and I'll illustrate what exactly I mean by that with an example. Documentation improvements, so I will just sort of very briefly show you we're working on a new version of the dref page. And if I were to open it up, you would see, well, that's really hard to read at this magnification, but you can see there are now lots and lots of sections, basic uses, symbolic functions, different kinds of functions, vector arguments, integral transforms. Also, if I open up the application section, then lots and lots of sections. And sort of one of the examples is sort of a friend of an example we saw earlier. So I have here a derivative, a function, I compute its derivative, and then I have here a manipulate where I show f prime of 5 and a secant line, and then as we bring the 2 points closer together, we see how the slope of the secant line approaches. So we have from very elementary sorts of functions like that to some very advanced applications. Some improvements. So we fixed a bunch of bugs and added a bunch of suggestions. So these are various, mostly number theoretic things. So sums of zetas and so forth. Yep, improvements to some. And we're currently working on improvements to integrate. There was a talk this morning about Mellin transforms and Meiergy. We're also making some improvements to how it applies the Newton-Leibniz rule. But index derivatives, this is sort of my last example. So we have certain functions which clearly indicate you're talking about an indexed variable. So if I have here an inactive table, this is sort of a position vector with components x of k, where k is some variable. Now, when you differentiate that with respect to xj, you don't want that to be completely 0 because there's no xj here, except you sort of assume that xj could possibly be one of the k's. And so what we've done is for these functions like table and sum, we now recognize that an x of something may be an index and handle that appropriately. So if you take the position vector and you differentiate it with respect to xj, you get a Kronecker delta. Either j and k are the same and you get 1, or you get 0. And a similar sort of formula if you take the norm of that vector, so that's the sum of xk squared, and differentiate that with respect to xj. And in order to get a nice simple answer, I explicitly say that j is an integer and k is between 1 and n, then you get 2x sub j. And I will just say that as a geometer, I don't believe in the existence of a position vector, which is why it's in sarcastic air quotes. This sort of index differentiation is obviously near and dear to my heart as a geometer, but is useful in very, very many areas. So that is very likely to make it into 11.1 as well. It's a little bit further out than the nth derivative stuff. And so that is what I had to say. Devendra, is there anything else you think we should mention?
Just to mention that the work on sums was done by a first-year undergraduate from CMU, who was an intern with me. He fixed 300 suggestions in 2 months, and he got a writing paper on number theory. We have worked through Stewart's calculus textbook, 4,000 examples so far.
Yes, a lot of these examples in the new DREF page, I mean, some of them are obviously original to us, but some of them are, solutions to actual problems from Stewart's book. So I don't know how. What's that? Adapted from. Yes, I guess Stewart might object if we had solutions to his problems in our documentation center, but but yeah, it's a very nice collection of examples, so I think you'll be quite pleased. And certainly as we add to functionality to each one of these basic calculus functions, I mean, we're now starting to work on integrate, and hopefully we'll get to limit in the not too distant future. We'll be updating the documentation for each of them so that it meets the same standards of all the newer functions, which were written later and therefore got much fancier documentation pages. So, question?